All right, Kevin. So we've learned a little bit about the history of the CubeSat. We learned about some interesting and early CubeSat missions. So this Minisode number 3, we're going to start getting into some more of the technical components of the CubeSat. Is that right?
Yes, we're going to look at why we go to space, common mission types, and then we're going to jump in and do a very quick survey of the major subsystems in a typical CubeSat.
So subsystems. So in other words, before we even get to that part, just so I understand, the CubeSat has all these different components that you have to construct before you can actually send it up.
That's correct. Much like in the human body, you have organs and you have different systems like your digestive system. The satellite has corresponding subsystems that each have unique functions that enable it to accomplish its mission.
Got it. Well, let's go ahead and get started.
All right.
So we use CubeSats to go to space. Why are some of the reasons we use them to do so?
Well, CubeSats have a number of really relevant missions today, with the lowering costs, the cost of launch has gone down, the access, the number of vehicles that can carry CubeSats, and the technology that we can put in a small form factor have really enabled us to accomplish a lot. But let's start with, if you're interested in CubeSats, I put together a quick survey of 5 sources. These are sort of your must-haves if you're interested in CubeSats. So if you look at the left there, NASA puts out about every year or so, every year or 2 years, the small sat or the small spacecraft state-of-the-art book. Fantastic. It literally lays out all of the subsystems that I mentioned, that I will mention today, and some others. Another NASA document is it's a guidebook for technology development projects. And you can find all of these online.
Well, that's what I was going to say for our listeners who can't see the screen, of course, they can just type these in.
The third item on my list today is the CubeSat technical specifications. You can find those at cubesat.org that literally tell you about the official size and dimensions of the CubeSat, as well as the deployer data. The fourth reference I want to mention tonight or today is the CubeSat 101 booklet. It is the beginning document. It was made by NASA about 2017. It first came out specifically for first-time builders, first-time CubeSat developers. So if you just Google NASA CubeSat 101, you'll get a nice PDF that you can download. The final reference I want to mention this evening is the NASA Systems Engineering Handbook. So I recommend, if you're working with students, if you're working with rookies, you lay out the mission, right, and all the phases, and use this engineering handbook as a guide to help you as you train your students and they build their spacecraft.
So these are references you would be recommending to educators who might be learning or working with their students to teach them about it. But are these materials things that you actually use with your Wolfpack CubeSat development team?
I definitely used 3 of these from day one in 2015 when I first started with middle school students. The CubeSat 101 book did not come out until about the time we were selected, but I've used it since, and that was 2017. So absolutely, these are, I'm speaking from firsthand knowledge here.
Got it. So just as a reminder, those who are members of the Wolfpack would have access to these documents as well if they were part of our.
They most likely already have a shared folder.
Joining, right?
Yes, they already have a shared folder of these documents.
Understood.
Okay, so let's move on and talk just briefly about what are the primary missions of CubeSats. And I made a short list of 4 major categories.
Right, and we referenced these a little bit in the previous episode, but let's do a quick review of those.
Okay, so primarily today, most of the economy in space that's made from small sats come in 2 different types of missions, primarily communications and remote sensing. So
communications be like our cell phone technology,
correct.
like,
transmitting information to you. So larger satellites, you think about our cell phones, right? And our internet.
Our OnStar in your car.
All of that,
GPS
yes.
everything.
Even your ATMs only work with satellites, but those tend to be larger. Now, where your CubeSats are already making money for companies are in the areas of say, remote sensing,
Mhm.
because we are now able, with these constellations of CubeSats, to image every piece of land on the earth multiple times a day.
So I think that I've heard you talk about remote sensing, like in areas where there might have been some kind of catastrophe or some kind of issue, like say like I don't know, like not
Well,
a hurricane, but like the devastation that comes
sure,
after a natural disaster.
Well, think about it. Any area that's hard to get to, where something has created some upheaval, think volcano, forest fire, hurricanes, any kind of natural disaster, having on-site, high temporal resolution imagery is important.
Would we use them even like in war conditions too? Like if we're in the
Oh,
desert trying to
absolutely.
look for,
Absolutely. Without
different regions.
Desert Storm in
Right,
91 was the first war that really was called the space war, because we relied on GPS to move hundreds of thousands of people through the desert quickly and efficiently right to the spots. And secondly, we use GPS for guided ordnance.
I bet they probably used that in the hunt for
Bin Laden.
yes, thank you.
I'm sure GPS was involved with that.
So,
So two major missions, communications and remote sensing, but there are two others that are really important too. One, science payloads. So let's say you're carrying an experiment inside your spacecraft. It could be material science, it could be biological, it could be physical sciences, it could be space weather, but that sort of falls into remote sensing. But we do a lot of atmospheric science. So the bottom line is, I want you to think about lots of science missions get accomplished on spacecraft and at a much lower cost than if you had to send an astronaut to the ISS or in a free-flying spacecraft.
right. So so I can kind of reiterate that back to you, essentially, they might want to test something that they'll use for something more important in a larger mission. They can do it here to see if it works in the confines of space before they do that.
You sort of leaned into our fourth talking point, which is validation or verification of new components.
Right, that's right.
So those are the four that I wanted to mention. You primarily see satellites, especially small sats, doing communications, but remote sensing, communications, remote sensing, science payloads, and then they are also used to validate or verify technology or a component you might want to fly on a larger, more expensive satellite. So those are our four missions. Now, next thing I want to cover with you is, very quickly, all spacecraft are basically just divided into two parts, right? You have the payload and you have the bus. I want you to think about the payload as, why do we go to space?
Is that the same thing as the four missions that you mentioned before?
Absolutely, something, right? One of those themes that I shared with you is probably most likely the payload. Our personal experience, we flew a novel type of battery. That would be a material science payload. Some CubeSats look at the atmosphere and the space weather, and that would be remote sensing. But that's the why you go to space. That's your payload. Everything else on your spacecraft is called the bus. All the accompanying subsystems to enable you to accomplish your mission statement, whatever that may be, that is your bus.
So it's kind of like how you're getting, can I think about it like a school bus? This is how I'm getting all of my payload there.
Well, if your payload was to
bus.
get a child to school, then the bus would accomplish that. All right, so what we want to do in this session, just very briefly, is review these major subsystems. For those that might be watching this vodcast on YouTube, I have a slide with about 9 areas we want to hit very briefly, just so that when you start to do your research and reading in those documents that I shared with you, you will have an idea of what to expect. So the first one is we use the abbreviation EPS, or electric power system, which is really just the power subsystem. Without power, your satellite is dead. For instance, one of the first things that a satellite will do once it's deployed, either from a rocket or from the ISS, is it will, NASA rules require it to drift so far away, and then it will begin to power itself up.
Now, is this where like solar comes in, batteries, like, so you have different options? How many options are there for power?
Primarily on CubeSats, we only see batteries and we regenerate or we recharge those batteries with solar. So I want you to think about really the primary means. If we're going on like Voyager and it's going outside the solar system, they're going to use a nuclear power plant because you don't have enough sunlight, or you cannot build solar cells large enough once you get beyond Mars or
You
the
mean
asteroid
nuclear
belt.
within the actual
It's a nuclear
spacecraft
power
itself?
plant, right? And so the decay of this nuclear, these isotopes generates heat, and that heat can then be used to create electricity. So, but what we rely on entirely with CubeSats are batteries that are recharged. So they're just storing the energy that we harness from the sun. So with a 1U to a 3U CubeSat, think a softball box to a loaf of bread, they generate from about 1.2 to 20 watts of power. And what the variability there is if you deploy additional solar cells. So if you only have the area of the faces of your CubeSat to put solar panels, and your solar panel, your spacecraft tumbles, there are times that you're behind the Earth and you're eclipsed and you don't get sunlight. And then there are times you may not be pointing, your solar panels may not be pointing directly at the sun. So your wattage can vary.
Are there elements or some kind of things in space that might affect whether or not the power would kick on the way it's supposed to? Like, I don't know, radiation or like things like that that might affect the performance of the power source?
That's an interesting question. Now, if we think about it, all sunlight, everything coming from the sun is either a particle or electromagnetic radiation. So we have designed solar panels that are particularly useful with certain visible wavelengths. And these solar cells, now the technology has advanced till we're about 33% efficiency at capturing that solar energy and converting it to voltage or storing that energy in our battery. But the bottom line is radiation, it may damage our software or our hardware, but it doesn't really interfere with our collecting of the solar energy. So that's power number one. Second, guidance, navigation, and control. You'll often hear satellite folks use the phrase GNC, and that's what they're referring to. GNC, very simply, is where are you in space? Where are you going? And if you're remote sensing, what exactly are you pointing to? And in addition to knowing that information, being able to control and point yourself, especially if you have a camera or a radio antenna that only works within a really specified angle. So if you think about it, we also use another acronym called ADAC, and ADAC is Attitude Determination, Attitude Control. So that's guidance, navigation, and control. Think about thrusters. Think about chemical thrusters.
Right, that makes better sense. Now I'm starting to understand. So this is how it's going to, it's not the same thing as propulsion, because I see we're going to do that later, but it's how it's in a way that it's going to be moving.
Think about stability and pointing. Being able to point to your target if you're taking pictures.
Is this something that you have to program like a computer program
well,
to be guided, or
that's a good question. There are a few ways that we can do this. I think one of the coolest ways is we have these conductive coils called magnetorquers. That's one way. And if you run a current, if you have a current that is moving, right, a moving current in a circular path, you actually generate a magnetic field. And then you can make your spacecraft's magnetic field, it will react to the Earth's magnetic field and either be attracted or repelled. So those are called magnetorquers. Another way that we control the attitude, if you will, think about the way you're pointing as your attitude or your stability, is with control moment gyroscopes. So if you've ever seen a gyroscope spinning, you know it wants to stay oriented in a particular direction. So imagine if you have 3 gyroscopes, each at 90 degrees to one another, you can use those to create moments within your spacecraft that make it want to turn. So, and there are 2 other ways that you can control the attitude of your spacecraft. One is with reaction wheels, and the other reaction wheels, think about sitting in a chair and someone spins the tire and you twist the axis of the tire and it makes the chair spin one direction.
So it's likely that whatever you're choosing might have elements that pop out in some way or like unfold.
No, these are all
later,
internal.
Okay,
These are all
so
internal.
Do
In
this,
fact,
do these add to the weight then?
always one of your considerations that you always have to deal with are size and mass and power consumption and data budget.
Okay,
All of those are important. I will tell you the simplest, easiest way to semi-stabilize your CubeSat. If you don't need to point towards the Earth and you have a small CubeSat, what we have done is we put a permanent magnet in the center of our CubeSat. And so as it goes around the Earth, the magnetic North Pole of the CubeSat is oriented towards the South Pole of the Earth. And what happens is it only flips once at the poles. Now you also are free to rotate at 90 degrees to the direction of travel, and that allows for some distribution of heat. So you are allowed to tumble in that way. So another way that we keep track of where we are or where we're pointing is there are devices literally called star trackers. So there are cameras that can image the space, and by seeing familiar constellations, it can know exactly where it's pointing. Also, there are sun sensors that can tell if it's in the sunlight or not. And we often use those to tell us, hey, we can turn on our radio now because we're not going to run our batteries down if we're on the dark side of the Earth. And there are also horizon indicators and atomic clocks. So that's it for a quick review of guidance, navigation, and control. Let's move on to the third subsystem, which is simply comms or communications. So the joke in CubeSat land is that if your radio doesn't turn on, you basically have orbited a piece of space debris, because we need our radios to talk or we don't get any data. It's the data that we need to help us accomplish our mission.
Well, obviously you have to test all of these before you go up, but is there something that would prevent, if it worked on the ground, is there something that would prevent the comms from turning on?
I think commonly, if you've tested your radio on Earth, things that might go wrong, perhaps you had some vibrational damage, when you were launch. It's very important to build a satellite to withstand whatever vibrational load you're expecting during launch. That's probably the most important. But very quickly, the components you want to think about as you look at your comm system are an amplifier, first of all, an antenna and a transceiver, which can both send and receive a signal, an antenna, and then of course, you may need an amplifier. These CubeSats have very small antennas. And for instance, the satellites we work with are either simplex or duplex radios. A simplex radio means it is basically receive only, and a duplex radio can transmit and receive.
Okay, but I'm still having this vision, right? Of like, imagine a little TV box is my CubeSat, and I have all these things that you've told me now are inside, right? They're not, and they don't like unfold and come out in some way so that they're on the exterior. So where is this antenna? How is it not, like, I'm picturing a little TV box with like something sticking out.
So there are two major types of antennas that I'm familiar with and have a little experience with on the CubeSats. One is called a ceramic patch antenna. It is literally about 1.5 centimeters. It's less than an inch on a side square. It's probably about a 1/4 inch or 5 millimeters thick, and it sits right on the face of the CubeSat. That's one type of antenna. Another is like a metal measuring tape that you would extract out, and it's curved and it bends, and you can deploy those antennas. So there are two kinds of antennas. Typically, the patch antennas are not deployable, and then the whip antenna that you might think of like a metal tape measure, those are also very common. Yes, we deploy them on orbit. So typically CubeSats or satellites use, large spacecraft will use a Ku or a K or a Ka band. Those represent different frequencies. The CubeSats that I've used, we tend to be in the 1.6 gigahertz range on the frequency, and that's in the L band. The CubeSat we talked about last episode, Marco, that went to Mars, it actually used the X band. It needed a different band.
So there must be, so we're talking about then the receiver of that communications is something on Earth that has to, almost like a channel on a radio that goes to those bands?
Correct. You build antennas and you tune your antennas to listen for certain frequencies. So imagine if you have a tiny radio and not a lot of power when you send out your signal from your satellite, you often need a larger dish to collect that signal on Earth because you can't, the satellite only has so much power it can put into its radio. So that's a quick review of comms. Three major components: your antenna, your transceiver, your amplifier, and the wavelengths. The government determines what wavelengths a particular operator can use.
Is this where you have to work with like the FCC and all that too?
That's right. One of the scariest things about a satellite is vibration testing and dealing with the Federal Communications Commission to get your license for your radio, because you cannot load your satellite on a spacecraft if you don't have a license.
Can ham radio people pick up on these comms?
Actually, the amateur radio folks, as we may have mentioned earlier, they were very important early on in listening for CubeSat transmissions, and they'll often record them and then share with the owners. So our next subsystem is CDH, command and data handling. So I want you to think about avionics. And in general, there are three areas you want to think about. Software, you want to think about the software that runs your satellite, your command, the architecture of how data gets handed from one subsystem to another. For instance, how does your payload know how to talk to your radio?
What exactly is avionics, just to be clear?
Think about it as the processor or the computer, the brains of the CubeSat. Think of it as the nervous system, the brain and the nervous system of the satellite.
Okay.
It manages the data. And because we're in space and there's more radiation, we often need components that are hardened to radiation or are tolerant to upsets and can reset themselves.
So I'm imagining like a motherboard kind of thing on a computer.
Well, actually, a lot of our subsystems are made on printed circuit boards.
Oh,
so
right.
that circuit board is something you're probably familiar with. It's sort of green and layered, and there's circuits at different sections of the PCB, but absolutely we use printed circuit boards. Okay, so that's 4 down, and looks like we have about 5 to go. So the rest will probably go a little bit faster, but let's talk about structures and thermal management. So structures and thermal management. Think about the chassis. We often use the word chassis to describe the external.
That makes me think of a car. Is
That's
it
right.
similar?
Yeah, like the frame of your car. So we used often anodized aluminum coatings and anodized aluminum, and then we have coatings on many of our components. And the aluminum needs to be strong but light. Remember, we're always worried about mass and size. Well, mass and weight, we sort of use that simultaneously or interchangeably, but size, mass, and power and data. So we can use coatings to help protect some of our electronics, and definitely with shielding against radiation. As I mentioned earlier with the avionics, we can use aluminum and titanium alloys. And one of our students actually was interested in polyethylene as a potential, barrier for radiation, and because space has a lot of particles and EM radiation. The good thing about your structures, if you're going to do your own satellite, build your own satellite, there's a lot of commercial off-the-shelf parts. Even polylactic acid, which is a common filament in 3D printers. You have to make sure your components don't outgas a lot. They do provide the properties you want. Another 3D printer filament, ABS, is sometimes used, or nylon. And composites are very popular because they're really strong and very light. And some of the most interesting stuff going on are thermoplastics, where you have something that's, light as plastic, strong as steel. So those are interesting as well.
And did you say those could be 3D printed with those?
Some components,
plastics?
well, some components can. It depends on where your satellite is going. If your satellite stays close to Earth, doesn't have a big heat, it's not producing a lot of heat, it's quite possible that you could have some plastic type components, but you're always careful about outgassing and the temperature range. And what will your
and what's outgassing?
outgassing happens when you take something. So right now we're at 1 atmosphere, we're at sea level. And the atmosphere is pressing on every square inch of your body with 15 pounds of weight. If you think about it, that's the weight of the atmosphere above you. When you go up to space, there's no arrows, there's no pressure pressing on any surface. So sometimes materials like adhesives, tapes, things like that, they will start emitting gas that otherwise would have stayed in that solid material. And that becomes a nuisance for other people. And NASA is very particular about the amount of what they call volatile materials on your spacecraft. So as we talk about thermal management, you can do that. You can control the heat of your spacecraft a number of ways. Number one, you can, sort of barbecue roll your spacecraft where one side isn't always facing the sun, but there are also paints and coatings and shield and tape. Those are ways that you can just build in some structures to move some heat. Everything in a spacecraft, in the simplest terms, is radiation. We can't do convection or conduction. In your larger spacecraft, you can have heat pipes where you have a liquid that's in a tube that moves heat from one side to another. You also have coolers. We have cryo coolers for subsystems that have to be kept at a really low temperature. So that covers thermal
Would you need
management
those for things like biological payloads?
So it would depend, right? If you're going to fly things in an Earth environment, you're going to have to pressurize it to 1 atmosphere. You're also going to need to control the temperature, which may mean you need heating and cooling. So that takes us to our last couple of items. When you integrate your spacecraft, you can't just staple it onto the side of a rocket. You can't give it to an astronaut in a duffel bag. It has to go somewhere. If you're going to deploy directly from the rocket, you're going to use some sort of P-pod, some kind of deployer. NanoRacks makes a deployer. Tyvak, I believe Tyvak had the P-pod. But the bottom line is, if you're going to be injected into space, either from underneath a rocket down near the rocket bell or up top as on an ESPA ring, secondary payload ring, you've got to be integrated. So typically when we think about integration, that is really interfacing and loading your CubeSat in its pre-launch configuration.
So that's when you travel to the location where it's going to be set in that deployer, right? So when you say you're going to an integration, that's where they're going to take your actual CubeSat factor form. It's not really a form factor.
It's a CubeSat.
Right. It's ready now. It's got everything in it. It's got all those parts, and you're going to put it into the thing that's going to deploy it. So that's integration.
Right. Yes, that's integration. In 2018, with our first CubeSat, we went to Seattle to do that with Space Flight Industries, and that was such a good time. Very memorable. And I know that a couple of guys went to Houston for NanoRacks for CapSat.
Did Theo have to do this one recently?
Theo could not go because he was taking testing.
But
Daniel
did
that's
for
right.
it, and it was the ESPA ring thing.
Right. We took actually our third mission is a hosted payload, and an 8th grader conducted integration in Indiana at Near Space Launch for CubeSat, which should fly in the 4th quarter of 2023. All right, we're down to just 2, propulsion and deorbit systems. So let's talk about in-space propulsion. Very interesting as the technology's matured for smaller spacecraft. Bottom line is there's 3 kinds of propulsion: chemical, electric, and propellantless. Now, we measure the efficiency of a thrust. Thrust is the force to move your rocket. We measure thrust with a unit called specific impulse. It has a unit of second, but what it really means is how much push do I get for how much fuel do I use? So it's sort of like a ratio. And chemical rocket engines give us a specific impulse of about 100 to 250. And I'm sharing that with you, even if you're not certain about what specific impulse is, to compare it to electric, which is up and coming, and we're very interested in it. Because if you use ion or pulsed plasma or some sort of vacuum type system, a vacuum arc system where you're ejecting plasma or electrons or really high speed particles, you can increase your specific impulse by a factor of 10 from about 200 to 2000 seconds. So that's really good. To give you an idea, the Falcon 9 Merlin engine, I believe, has a specific impulse of 365 seconds. So we're talking about multiples.
So this is after you've been deployed and now you're out there.
Right,
You're not
it's-
just floating and you're
That's
not
right.
just using the navigational directional things that we talked about.
Right. It's
with
called in-space
GNC.
propulsion.
So this is something that's going to keep it moving. It'll make it move faster than it would if it were just going on its own.
That's
through
right.
space.
So if you think about propulsion,
But why does it need to go faster? Through
because
space?
perhaps it was offloaded at not its final spot. So imagine this. Rocket launches and we have a communication satellite and it needs to be in geostationary orbit, which is 38,000 kilometers above the Earth, but it gets unloaded from the rocket at 5,000 kilometers above the Earth. It will have to use its own engines to raise its orbit to get to its location. Finally, let's talk about propellantless. Imagine thrust without propellant. There are three kinds. You can have an electrodynamic tether. Imagine something that gets extended away from the spacecraft that creates drag by picking up charge in the atmosphere. Aerodynamic drag, think about a chute or a sail, if you will. Solar sails, aerodynamic drag, and tethers. Those are three ways that we can do propellantless propulsion. So that brings us to our last topic, which is, let's say your mission's done and we are worried about debris. We are really getting to a tipping point of things in space. How do you deorbit your system when it's at its quote end of life so that you free up that lane or that orbit and you don't risk or jeopardize other vehicles or humans? So there are three current technologies you can use to deorbit your spacecraft. One's called a boom, one is called a tether, and one is called a drag sail. So they're all means to increase sort of your profile. And even at 500 kilometers above the Earth, there's a few particles and there's solar pressure that pushes you down a little bit. So you end up losing orbit, but these tools will help you deorbit quicker. And they're important technologies in the future.
Well, I understand the idea of getting out of the lane, but isn't it still debris just because it's not in that same lane?
So what we're talking about is you're at a certain altitude. Let's say you're at 500 kilometers above the Earth. If you do nothing, your spacecraft will remain there for years. But if it's at its end of life and you can increase its drag, and instead of it being on orbit for 20 years, you can have it deorbit in 2 years, that's a win.
I still don't understand how it's not debris just because it's not in that lane. I understand it makes space for more that are going to orbit.
So eventually it's going to burn up in the atmosphere.
Okay.
Yeah,
So,
when we talk
but
about
it won't burn up
deorbit,
if it's in orbit.
no, it will eventually, for the most part, it will take 10 or 20 times longer.
Okay, but it will go faster if you
That's
take
right.
it out.
What
Why? Is
we're
it because it's going faster when it's in orbit?
So all spacecraft go faster the lower they get in altitude, the closer they get to Earth. But what we're talking about is we want to decrease the amount of time it takes for the spacecraft to reach the upper area of the atmosphere, which means it's a point of no return and it's just going to burn up. And it can't hurt anyone if it burns up, because we intentionally build spacecraft without materials with high melting points. So aluminum is better than tungsten because aluminum has a much lower melting point. So we volatilize our spacecraft. And if you have a small CubeSat, none of it reaches the ground at all. It ends up vaporized. So in summary, we've covered 8 basic subsystems, and they all fit together just like the systems of the human body does to create a healthy organism. And all of these subsystems exist for one reason, and that's to help the mission owner execute the mission that they have.
And to receive whatever data it is that they're testing.
Well, the data would be the evidence, that would help them get the answer to whatever question they
that
ask.
they're seeking.
Right.
Well, that's a lot, but I think it does a pretty good job of helping to understand why you might need those manuals and handbooks that you mentioned at the beginning. I would imagine within those resources, it helps you walk through the construction or the design of these subsystems. Yes.
Absolutely. And And I just want to add that no one, builds a satellite on their own, and the community is very good about helping one another. And there's so much content out there. As we are recording this, we're getting ready to go to the SmallSat conference, and we're expecting to hang out with 4,000 CubeSat builders in the next week or so.
So you could go there theoretically if you're looking for these subsystems and find companies that.
That's exactly how
that.
I did it several years ago when I knew absolutely nothing except that I wanted to build a CubeSat. I started by going to SmallSat and meeting and talking with as many people as I could.
Mhm.
This year we have 6 students going, and I have no doubt they will come back with their own visions and missions that they want to execute in the future.
Oh. Well, what can we expect for our next lesson, our next mini-sode? So we've learned about the history and different kinds of interesting CubeSat missions and now payloads.
I think our last installment is going to be really focused on what is the future of CubeSats. What is their future with respect to constellations? There are a lot of companies that want to put up lots of constellations. Some of these are microsats, but some are CubeSats. And third, what would be some interesting student payloads? So what are the Wolfpack students proposing to fly?
All right. Sounds like we'll be talking about the future in the future. So join us next week as we say,
Let's go to space.